Welcome back. This episode I'm going to look at polarity, that is polarity of bonds in covalent molecules themselves. First of all, just a bit of a recap on types of bonds. Now we know that ionic bonds occur when atoms of different ionization come in close proximity. We think of a metal combining to produce positive and negative ions. The metal will give up its electron quite readily, and the non-metal will accept the electron from it. They then form oppositely charged ions and will attract each other. A covalent bond occurs when the valence electrons of two neighbouring atoms are shared, and the bond is the mutual attraction of the positive nuclei for this shared pair of electrons. Now these electrons will be shared when you have two atoms of similar ionization energy in proximity. Normally we think of non-metal atoms doing this type of bonding. Now ionization energy, as we saw in a previous episode, is the energy required to remove loosely held valence electrons from an atom. A similar property is how well those atoms can attract or hold electrons when they're bonding. We call this property electronegativity. Atoms are given a value of electronegativity, with fluorine being the atom with the highest electronegativity. It attracts electrons very, very strongly. I mean, it would steal electrons from its grandmother given the chance. And as you go across the table to the left, you'll find the electronegativity decreases as you go to the metal side, and it will also decrease as you go down the table. This graphic just shows the trends of electronegativity. There are other types of graphics that you can find on the internet too. Here's one which is showing a three-dimensional view of electronegativities. The values don't have units, they're just a relative value of electron attracting ability. Now to determine which type of bond is going to be formed when two atoms come near each other, we look at the differences in electronegativity. A small difference will produce a covalent bond, whereas a large difference, something more than 2.1, will produce an ionic bond. If the two atoms in a covalent bond have identical electronegativities, and that's only going to occur when they are identical elements, well, they'll share the electrons equally. So if you had two oxygens or two chlorine atoms forming a diatomic molecule, the electrons would be evenly shared and would spend equal time at either end of the bond. Neither end of the bond will be more negative, and that symmetrical bond is known as a non-polar bond or purely covalent bond or pure covalent bond. However, if two atoms bond, two non-metal atoms bond and form a covalent bond, and they have different electronegativities, you'll find then that one atom will have a greater share of the electrons than the other one. It'd be like if you were sharing a block of chocolate with a younger sibling. You both share it, but you'd probably get a bigger share than they would. And the same thing happens with atoms in covalent bonds. So you'll end up having an unsymmetrical bond with one end which is slightly more negative than the other, because the electrons spend more time at that end of the bond. That bond is said to have a dipole. Di meaning two, that means there are two ends to it, a positive end and a negative end, and it's called a polar bond. It's represented by an arrow as shown in this graphic, and we put delta negative and delta positive to indicate that there is a slight negative end and a slight positive end. It's not as positive and negative as an ionic bond is, but it is slightly negative and slightly positive. Here's an example of a polar bond in a diatomic molecule. Now the molecule is hydrogen fluoride. The bond is such that the electrons will spend far more time at the fluorine end of the bond than at the hydrogen end. In fact, if you look at the electronegativities, this is probably one of the most polar bonds you could get. Fluorine has an electronegativity of 4 and hydrogen has an electronegativity of 2.2. So you'll see that the fluorine end of the molecule is slightly negative and the hydrogen end of the molecule is slightly positive. So not only do you have a polar bond, you actually have formed a polar molecule as well. Those examples that I've looked at were diatomic, and there's only one bond in a diatomic molecule. So if the bond is polar, then the molecule will be polar. If the bond was not polar, then the molecule wouldn't be polar. And there's an example there with chlorine. If a molecule has more than one line of symmetry, it will be nonpolar. And here are a couple of examples. We've got BF3, CCl4 and CO2. In each instance they have polar bonds, but because they are symmetrical, you find that the whole molecule is overall nonpolar. The polar bonds tend to cancel each other out. There is no dipole, there's not one positive end and one negative end to the molecule, so we don't say that they're polar, they are nonpolar molecules. If, however, a molecule has only one line of symmetry, it will be polar. So examples I've got here are things like NH3 or H2O or CHCl3. Now, in each of these instances, you'll notice that all of the polar bonds will combine to produce one end of the molecule being slightly negative and one end being slightly positive. When I mention one line of symmetry, you'll also notice that that dipole runs through the line of symmetry in those molecules. I've got an example here how the shape and polarity can influence chemical and physical properties quite a bit. I've got a trans molecule and a cis molecule with identical chemical formula. The cis molecule is very, very polar, and you'll notice that its boiling point is quite a bit higher than the boiling point of the trans molecule. So it is really important, this concept of polarity. In the next episode I will look at how the polarity of molecules will influence these intermolecular forces.